And then the rest of the parameters are irrigation, soil, and water loss. So to go over those parameters, first we have to get soil data for the Northern High Plains, the region we were looking at. So we use the Web Soil Survey database to see like what the soil composition is. And there, the composition can have so many different types of soils and combinations of soils. So we basically made the decision to choose like the one with the highest percentage makeup because we thought it would be a good representation for what we're doing. So what we chose for Hartley County was Dallam Loamy Fine Sand with a 0 to 3% slope. So the extent of the county was about 12%. This was the largest percentage that we could find. The hydrologic group is B, and then we basically have like the soil layers. There are 4 different layers here. And then it also gives us the available water capacity, which is important to project irrigation demands. Okay, so then we have our crop irrigation soil parameters. Basically, the main thing is that for the carbon dioxide levels for each data range, we had a different ppm concentration for CO2. So we're 363 ranging all the way to 524, depending on what climate scenario we were modeling. Already went over the crop growing season. The irrigation system we used was just multiple sprinklers at about 75% efficiency. And then we already went over the rest of the information about the soil. Okay, so now we're going to go over basically the results that we found. So IMAN-SYS gives you many different outputs, and we just chose the ones that we thought would be accurate reflection of what we did and most relevant to the study. So that's why we graphed the total gross rainfall and the crop evapotranspiration. So basically, the first 2 columns that you see, so the 1980 to 2010, that's just there to give us what the baseline conditions are so that we can compare the rest of the time series to that one. So as you can basically see, the gross rainfall is gradually increasing for the low emission scenario and the high emission scenario until you get to 2080. And then the high emission scenario shows that there's an extreme drop in the gross rainfall, which is not a good thing. And then crop evapotranspiration also is gradually increasing for both the low and the high end scenarios. And as you can see for the 2061 to 2080 projection, there's an extreme drop in the gross rainfall for the high emission scenario and an extreme increase in the crop evapotranspiration. So that's also not a good situation. So then the net irrigation requirements I would say it's kind of like a water budget. It takes all the demands and everything into account to see how much you're going to have to irrigate the crops. And once again, compared to like the baseline scenario, the net irrigation requirements are increasing for each time range and for either scenario. And especially by 2061 to 2080, there's a huge jump for the high emission scenario. And despite the fact that, if we go back here, despite the fact that rainfall was increasing, we're still seeing higher demands for net irrigation requirements because at the same time that rainfall is increasing, the evapotranspiration rates are also increasing. So there's not enough rainfall increase to keep up with the evapotranspiration rates, so we still have high irrigation requirements despite the rainfall patterns. So these are our primary findings, like overall, and then here is just a visualization of the monthly net irrigation requirements. And as you can see, I'd say for May and June, the monthly requirements don't seem to shift as much as the hotter months, so July and August, and somewhat into September, the monthly irrigation requirements show more variability rather than the cooler spring months. So I guess the most important takeaways from our study is that there will be significant irrigation needs in the future. These models, they just show predictions. They do their best to predict what's going to happen, but it's obviously better to err on the side of caution because things can be way more variable than we actually put them out to be. So we're going to have irrigation needs because there is extreme variability in precipitation that we're seeing already. We're facing droughts already. Ogallala Aquifer is already being depleted. So it's better to begin optimizing water management strategies and irrigation practices and seeing how we can prepare for these future conditions. So future work could explore different climatic regions across Texas, kind of like that graph, the map that I showed earlier. All the different climatic regions, they have different, water sources. Some have rivers passing through them, some are deserts. So it would be important to like explore different regions, evaluate irrigation requirements for some of the other major crops grown in Texas, such as cotton, sorghum, winter wheat, and then maybe use different representative concentration pathways to see maybe, what other pictures could be painted. And so that's it for us. Thank you, everyone.
Question to Michaela and Mariam? Yes?
So, will change.
Mm-hmm.
And I was wondering, what are the factors, like human actions, that causing this kind of change? It caught my interest,
Climate change?
Yes. And also,
What are the actions that what?
I mean, human actions.
What are we doing to cause climate change?
Are the factors that, play to push this climate change? And what do you think are the, like, what, we humans could do for corrective measures? Like, did you look into such things?
Yeah. So I can give you like a baseline overview. So what do humans do to contribute to climate change? That's, I would say the biggest impact is, beginning from the Industrial Revolution is when you really see a kickstart in how they exponentially increase greenhouse gas emissions. So industrial activity, major corporations, I'd say, are probably the primary contributors to the greenhouse gas emissions. And it's also kind of difficult to, I'd say like climate modeling is just difficult in general because different greenhouse gases, like carbon dioxide versus methane, they behave differently in the atmosphere. So they have different time frames that they last in your atmosphere. They have different potency. So it's a little bit difficult to say. It's difficult to say anything with positivity, like when it comes to like which greenhouse gases are the worst, or like, okay, we're cutting down our carbon dioxide emissions, but methane is on the rise because they behave differently in the atmosphere. But I would say, in my opinion, major corporations, emissions, climate change, increased use of plastics, and it's just like a big, I don't know if Michaela has any other input.
Yeah, we could probably talk for days about
Yeah.
all of the different factors that play into it. I think pinpointing major corporations is a large part of it because where the conversation often goes is individual action. So we drive too much, we consume too much, and those are true. Those are certainly factors. But I think we also see that individual actions are only a part of it. We also need to be able to live in a world where we don't need to drive as much. So if we live in a community where, in order to get to the grocery store, we have to drive, we're going to do that. And so if you go a little higher level, designing communities where we can walk to the grocery store, where public transportation is reliable and safe and affordable, those are actions that kind of at a higher level can have a bigger impact.
Yes. Go ahead.
Okay, I was actually, you more talked about emissions.
Mm-hmm.
You, like, development acts, those factors to consider?
The technological.
Impact, like, we push technology so far.
Oh, okay.
I believe there are some, like, there are so many variables.
Oh, okay.
At play.
Mm-hmm.
Yeah, you're right. There are many multiple players or sources of climate change or contributors. So, another question, please.
Okay. First, thank you for the presentation. I have two main questions. The first question is about the model. You took only one county.
Yes.
And you are looking for a temporal change of 20
Across that county.
years interval. What are other spatial constraints for this kind of model? Spatial constraints. Yeah.
So other spatial constraints for this modeling aside from the county that we're choosing? So I think this, correct me if I'm wrong, Dr. Ferris, but this model is primarily focused on like local and regional localized counties. So you're saying like, what would it be if we modeled like wider spatial regions versus?
You are looking the time, I don't know what kind of parameter you are looking, 20-year intervals.
20-year
Yeah.
intervals, yes.
That's a temporal.
Yes, yes.
My question is, you want to apply for irrigation purpose,
Mhm.
yeah? That must be a spatial or local
Yeah, so like
area
how is it
constraint.
transferable to other
Yeah,
regions?
you only use also one county.
Yes.
So
Oh, yeah.
what are the potential spatial constraints?
Yes, so you're correct. So I mean, like I said, so because we're only looking at this one county, which is primarily because of the time constraint that we had, we were planning on looking at 3 counties across 3 different climatic regions in Texas. So like more along the coast, more along central Texas, because they showed climate variability, so that our results would be more transferable across Texas. But because of time constraints, we focused on that one. But you're correct, like it's not transferable, let's say, to like more East Texas because there are more rivers and lakes, and Ogallala Aquifer doesn't stretch that far, so it wouldn't be as relevant. So we didn't look into that, but it would be.
And maybe the second one is use also corn or maize as one of your model plants. Why
Yes.
corn? Because plants differ in terms of water use efficiency, they differ.
Yes.
Yeah.
Yes, so yes. So we chose corn because it was one of the major, so we had we looked at four primary crops. So sorghum, winter wheat, corn, cotton, and we just made like an executive decision as which one we wanted to explore. Some of the papers we read looked at other crops, so we were like, let's examine this one because we hadn't read a paper on it over the ones that we looked at. So we just thought that, let's see if we see any differences for corn as opposed to sorghum, wheat, or something.
Good job. Thank you. So, go to the next speakers. So, upload.
So the next speaker is Sarah Davila. So she's going to talk to us about the application of Comet Farm, a software developed by the USDA to estimate on-farm carbon and greenhouse gas emission across the Rio Grande Valley in Texas here. So as you can see, the topics are complementing each other.
So building on what we just saw earlier.
Can this come down?
Supposedly it can, yeah.
Okay. Hello everyone, my name is Sarah. I'm a civil engineering master's student at the University of Texas, and I got my undergrad in civil engineering from the University of Texas Rio Grande Valley. And today I'm going to talk about using Comet Farm to estimate carbon and greenhouse gas emissions across the Rio Grande Valley, Texas, which is deep in South Texas. So it's definitely different from a different shift of where they were doing this code, which is cool. So just an intro on like agriculture and their impacts on greenhouse gas emissions. The U.S. agriculture greenhouse gas emissions have increased 12% since 1990, and currently, as of 2019, according to the U.S. EPA, they make up 10% of all our greenhouse gas emissions. And the main greenhouse gas released from agriculture is nitrous oxide and methane. So methane, we all know, is from livestock, from ruminant animals like cows, goats, etc. And nitrous oxide is more related to management practices on soils. And so, because the U.S. population is expected to grow 1.8 million per year between 2017 and 2060, and because we know agriculture is not going to be going away anytime soon, it's important to focus and to try to find best management practices to reduce the greenhouse gas emissions produced by agriculture. So there's several conservation practices that you can do to reduce greenhouse gas emissions in your agriculture, plotted land, and livestock. And those are tillage operations, using cover crops, different irrigation methods, because irrigations produce energy and therefore greenhouse gas emissions. So that's more like an indirect greenhouse gas emission, and different fertilizer types. So I'm using the Comet Farm accounting tool, which is a tool that was generated by the USDA with collaboration with the NRCS and Colorado State. And that tool is very handy. It's a decision-making tool for farmers specifically, and it computes a full net greenhouse gas balance and future projections, specifically from 2001 to 2030. And it calculates a number of greenhouse gas emissions like nitrous oxide, carbon sequestration. Well, carbon sequestration is what helps, but all the other gases are like that. So nitrous oxide, carbon sequestration, carbon monoxide, carbon dioxide, and methane. But my study is specifically going to focus on just nitrous oxide and carbon sequestration. And so Comic Farm also works for a variety of land management. It works for animal agriculture, agroforestry and forestry, and cropland, pasture, and range. So again, my focus is going to be more on cropland. So my study area is the Rio Grande Valley, Texas. So Micaela and Miriam did a really good introduction on the climatic regions of Texas. It's very diverse. And it's a really good representation of what we see in the United States, which is why it's a really good place to study. And so my study area is the Rio Grande Valley, which is number 10. It's very deep in South Texas. And I'm specifically focusing on a four-county region. Star, Hidalgo, Lucy, and Cameron. The reason why is because they're very economically dependent on agriculture. So as of 2011, the RGV has had a state economic impact of 1.1 billion per year, $1 billion per year. And the first bill of cotton in the world is harvested in the Rio Grande Valley, as you guys may know. And three of the four counties are in the top 10 sorghum producers in Texas. So that would be Hidalgo, Lucy, and Cameron. And so their field management practices currently are conventional tillage and flood irrigation. So the objectives of this study is to use Common Farm tool, using the Common Farm tool, like how are tillage practices impacting greenhouse gas emissions in farmland different across the Rio Grande Valley. And so I will be using extensive tillage versus no tillage and seeing how that plays a role. And then using the Common Farm tool, how are fertilizer implementations affecting the greenhouse gas emissions in farmland in different areas across the Rio Grande Valley. So the way I'm doing that is I'm just adding 25% fertilizer and reducing 25% fertilizer across the cropland and seeing how that affects greenhouse gas emissions. So I'm using two different farming locations. It was originally three, but I had some technical difficulties because of time constraints. I wasn't able to complete third scenario, but that is going to be on my report. So if you guys are interested, you can look at my report. It's going to be better. And so I'm selecting two different farming locations across the Rio Grande Valley, and I'm using the three most dominant crops as crop locations in the model. And I'm using the USDA NRCS Cropscape for the historical cropland data. And that's also publicly available. And so I'm applying conservation scenarios using Common Farm. So as you can see, there's 5 different scenarios that I'm focusing on, which is no-till plus fertilizer, tillage, which by till I mean like intensive till, because there's different tillage practices, but I'm focusing on just like the two extremes, no-till and conventional till, which is intensive till. I'm adding the 25% fertilizer and then till, taking away 25% of the fertilizer and then no-till with fertilizer 25% and then no-till with fertilizer 25%. So this is a little bit, this is kind of just like a schematic of what I went through these past 3 weeks to kind of get to my results. So I got all of my data from a lot of manuals and recommendations from Texas A&M AgriLife Extension, which they have like a lab down there, and they do a lot of experiments, and they publish a lot of really easily accessible information for like farmers in that region, which is really cool. And then the USDA and the Texas Water Development Board also have some manuals, just like recommendations that I can use. And so all of that, I was able to extract crop yields of the region, cropland history, fertilization recommendations, and irrigation requirements from the years 2000 to 2020, because that's an input that you need for Common Farm. And then Common Farm spits out all of these greenhouse gas emission calculations, but I'm specifically looking at, as I said before, N2O emission, which is nitrous oxide, and carbon sequestration. So this is a little bit more in depth of like exactly what was going on in my head while I was running this Common Farm tool. So I used 3 different crop types just because there were the 3 major crop types in the Rio Grande Valley, as you will see in the previous figures. and the fertilization requirements were obtained from Texas A&M. And so I was just, and then the date planting and the date harvesting were also from the manual that I was able to get. And then I used fallow as a crop rotation. So whenever we're not in season of corn, sorghum, and cotton, we're implementing fallow, which is just bare soil. They just till it and they don't put any seeds in it. It's just left as bare soil. And so the fertilization type that I used is ammonium nitrate, just because I saw in some literature that nitrogen is very important for fertilization. And the irrigation type, again, that we're using because we're in the Rio Grande Valley is the furrow or flood irrigation. And they use approximately 2.86 inches every 7 days. So that's an input that. And so this is just like figures of like corn, sorghum, and cotton in case you guys had never seen it before. And then this is an example of what furrow irrigation is. So my first case study is an area in Mercedes, Texas called Ross Co. I just assume that 333 acres is like their plot of land, so I'm pretending that I'm a Ross Co. farmer, and I just want to see how I'm impacting the greenhouse gas emissions. So this is like a schematic of the crop history from 2000 to 2020. So they populate a lot of sorghum and cotton and corn, which is again why I chose those three crops to focus on for this model. And so this is the results that I got from Washington Co. So the baseline is basically like like it's just like a reference point for to kind of compare all the other results with. And so baseline, so like no change, it's about 11,477 vehicles driven per year. That's like how much greenhouse gas they're emitting into the atmosphere just by cropping and planting the way they're supposed to be planting, or like the way they are planting.
Business as usual.
Business as usual, yeah, thank you. Yeah. So no tillage, you see a slight decrease of 11,398 vehicles driven per year. But then once you start adjusting the fertilizer requirements, that's when you start seeing like the drastic changes. So like when you have tillage, like the conventional tillage, and then you subtract the 25% fertilizer, you get a really big decrease in net greenhouse gas emissions. And then as the same, if you take away 25% fertilizer, and you have the no-till situation.
Can you please walk us through the graph?
Oh yeah, so this graph, the bar line in blue is the carbon sequestration, so that's what the soil is helping us absorb carbon from the atmosphere, and the orange is the N2O, which is the nitrous oxide emissions from each of the scenarios. So as you can see, there's quite a variability among here.
So ideally, you would like to have.
Oh yeah, so it's an ideal situation. We want to minimize the orange and maximize the blue. Minimize nitrous oxide because we know that's a greenhouse gas, and maximize carbon sequestration. We want to absorb carbon from the atmosphere. So this is my second case study in San Benito. So again, we see that cotton, corn, and sorghum are like the dominant crops that they harvest there. And this is an area of 123 acres, so it's a little bit smaller than the previous one. And again, the results we see that we see kind of like variability among the nitrous oxide and the carbon sequestration. And so the baseline is like 5,076 vehicles driven per year. And versus, so again, we see almost the same results as from the previous one, where there's a really big decrease in vehicles driven per year with a negative 25% fertilizer, so taking away 25% fertilizer and doing intensive tillage versus no tillage. But it's interesting too because like tillage and no tillage with the minus 25% fertilizer, it's pretty much the same. So there's other considerations to look into, and that opens up a lot more questions for future study.
So which one do you think is the optimum here?
So that would be a really hard question, and you would have to kind of give this to farmers because they're the ones who want to say, oh, well, I want more carbon sequestration, or, oh, I just want, to minimize my, N fuel. And this is why it's the perfect tool for farmers, because they know exactly what they want from their farm. And, yeah, so this is a good example of, like, just the trade-offs, and so you can kind of see the results.
There was no carbon emission.
Sorry?
There was zero emission or sequestration. The carbon.
Well, from my understanding, this is just calculating like what the soils would absorb. I'm not sure about the carbon emissions.
So the model neglecting emissions or not emissions?
Well, in this particular case, it is not calculating them because I didn't put the input parameters for them just because the data availability was very sparse for me and it took me a while to just get all this information together. But that's definitely like a future study that I'm planning on.
Why the baseline is different from the previous?
Yes, and the baseline is different just because there's a smaller acreage. So this acreage is 133 and the previous one was 333. So it's like 200 difference. 200 acres of difference. So tillage practices affect the carbon sequestration as we had just clearly saw in the previous graph. So with less tillage, there is more carbon being absorbed by the soil because the soil is undisturbed. So the organic matter and all the other living things that help the soil be healthy stay, and they're not being disturbed by the tillage. And fertilizer management affects the nitrous oxide concentrations. And this is kind of like a straightforward answer because for the fertilizer that I implemented has nitrogen, so if there's nitrogen in the area, there's going to be some reactions in the atmosphere that create nitrous oxide. So implementing more fertilizer where there is no tillage can be overall not effective with net greenhouse gases. And I mean, these numbers are very close to each other, and so further statistical analysis would be recommended, but because of time constraints, I wasn't able to do that. But that's definitely something that I'm looking forward to doing, at least for my report. So limitations on future work. So Common Farm model needs to include more variety of crops because as we had seen in like one of the regions, sugarcane is very prominent in like some areas of the Rio Grande Valley. So, and there wasn't sugarcane in Common Farm, so it would be interesting to kind of just see like sugarcane. I know it has different management practices, but it would be cool to see like how that affects the greenhouse gas emissions as well. And data availability, again, like because I'm not a farmer and I don't have all of that information with me, it was really hard for me to kind of just find simplify my model to get some answers. But as a farmer, I know I'm going to know my cut of land at the back of my hand. I'm going to know what fertilizer requirement, what line implementation I'm going to be using. So this is just a very good and useful tool for farmers to have because they'll have all that data. They don't have to search for it. They'll already know what is in their land. And soil tests should be done at each study area for accurate fertilization requirements. So I didn't realize how complicated fertilization is. Like, it's different depending on the soil you're on and what you're trying to grow and everything. And if we're managing the fertilization requirements appropriately, then we'll be able to decrease greenhouse gas emissions as we get seen in the results. And again, I did not include lime, but I know lime should have been implemented into this model, but I didn't just because of time constraints. And yeah. So in conclusion, the reduction of net greenhouse gases, a fertilizer that contains nitrogen along with the no-tillage method is best, again in my opinion, but other farmers might want different things, and it's good to have all of that laid out in front of them so they can kind of see, pick and choose what it is that they want for their farm. And the no-till and decreasing 25% of the required fertilizer is second in reducing net greenhouse gases, but it overall has a lower carbon sequestration. So again, that trade-off. We got to see what it is that the farmers want. So decision making is necessary for implementing a farm management practice, as we already know, and as we continue to work together with farmers. I think Common Farm is a great tool for farmers to be more conscious of how management practices impact the greenhouse gas and carbon sequestration. So just like farmers knowing about this tool is enough for them to kind of explore and see how they can manage their plots of land or their crop land appropriately. And then with that, I'd just like to acknowledge Dr. Word, Ms. Kloppenstein, and all the PVA staff for helping me pursue my interest in the agriculture science. Thanks so much for your time.
Any questions for Sarah? You may ask if there is.
Oh, do you guys have any questions?
Here from the
Zoom people?
yeah, Zoom people.
Do you have any questions?
Sure, I have one.
Yes.
I was wondering, no-till, why don't people all do no-till? Is there a disadvantage to it? I don't understand what that is.
Yeah, so according to some literature and from my understanding, the no-till is just like when you're not rotating your crop, like when you're not moving around your soil as much. And I guess the disadvantage is that they just produce less yield because, or it's just like harder to manage because there's cover crop and there's other things growing in your plot of land, and people just want to create yield. People just want to produce food in their land.
Well, I might want to add a little bit, Charlie. That's an excellent question. No-till is a very common practice right now around the world. It has its own limitations, but it has also lots of positives. One of it is basically protecting the soil, increasing the carbon sequestration, improving the water quality, preserving the biological health of the soil. So there are a huge, advantages of no-till. But there are also some disadvantages. There's excess use of, not excess use, you need to use pesticides in order to kill some of the weeds, etc. So there are advantages and disadvantages, but in many, in opinion of many scientists, there are much more advantages than there are disadvantages for the no-till.
It's just a matter of communicating that science to the farmers appropriately, because some farmers very cultural and they just want to stick to their own ways, but we gotta help them understand that no-till is a really good management practice.
Any other question from our Zoom audience? If not, we'll go to the next.
I have a question.
Oh, I'm sorry.
Because about this reducing fertilizer, 25% reduces emission. How about the yield?
Yeah, that's a good question. I don't think Common Farm goes into depth of the yield. That's the yield is like an input parameter for Common Farm, so we can't really calculate what the yield would be. The yield difference would be with fertilizer.
Because farmers, they will not produce fertilizer analysis.
Yes. Yes, the yield is very dependent on farmers.
That's a good question. Thank you very much, and let's go to the next speaker.
And the next speaker would be speakers this time, Sophie and Kaylin. So they're going to be talking to us about the effect of organic amendment types and rates on sweet corn and Egyptian spinach seeds germination. So this is a joint effort between Prairie and University College of Agriculture and
UT Austin College of Engineering.
Hi everybody, so today we're going to be talking about our experiment investigating the effect of 3 different organic amendments on 2 different types of seeds and impact on seed germination. So the motivation behind this study was
the switch from inorganic fertilizers to organic fertilizers. And this is part of people wanting to be more sustainable, wanting to reuse waste from different industries in farming. So the main difference between organic fertilizers and inorganic fertilizers is, well, a few things, but one, for organic fertilizers, the nutrients that you apply to the soil have to be broken down. Some of it has to be broken down by microorganisms, so it takes a little bit longer for organic amendments to increase plant growth. So there's a time aspect, and then um, they also vary in the amount of heavy metals, salts, and other micronutrients. Whereas synthetic fertilizers, they're made for the plant. They include what they want to include and don't include any elements that could be toxic. So some of these heavy metals and salts can affect the plant negatively and impact seed germination. So prolonged seed germination, cause them not to germinate, impact the growth of the plant. So our overall objective was to investigate two different types of seeds, sweet corn and Egyptian spinach, and the impact of organic amendment types, 3 different types, and 4 different rates. And we did that by measuring root and shoot growth from the seeds. The materials we used, so like I said, we included 3 different types of organic amendments: chicken manure, malorganite, and dairy manure. Malorganite is a product of wastewater treatment waste. So it's treated and then used for fertilizer. And then 2 different seeds, sweet corn and Egyptian spinach. A similar study was conducted at Prairie View with collard greens, and they, in their paper, analyzed the composition of the 3 manures. So this was taken from the paper that has already been published. So they previously analyzed the pH and electrical conductivity of the manures. As you can see, the pH between the 2 extracts. So this is described in our method section, but we used 2 different extracts on the seeds. The first extract is just the manure mixed with DI water. The second extract is after centrifuging and removing the supernatant of the first extract, we add more water and use that. So the second extract is really to show the results if a farmer applies manure and irrigates right after. So it's more dilute, and you could rinse away some of the toxic metals or toxic elements that are in the manure. The pH remains basically the same between the 2 extracts. The electrical conductivity decreases a lot, so there's less salts. And they also did a more in-depth analysis of percentage reduction and increase for various elements between the first and the second extract. So for the most part, a lot of the elements, like we would expect, decrease in the second extraction because it's diluting.
So yeah, like Sophie was saying, we had diluted them with DI water and then put them in the centrifuge, and then we filtrated it, and that's all our samples was the second extract of them. And so first we had to label 200 petri dishes.
Only?
Only. And we put 10 seeds in each of them, and we did 4 replicas, and then we wrapped it with the paraffin, and then wrapped it in foil and put it in a drawer. And then this is us measuring them. We did it in millimeters. And you have to do the measure the shoot and the root. So this is just an examples of like basically what's shoots versus a root.
You can use the mouse if you want. You can use the mouse.
Oh, use mouse. So this right here is the shoot, and then this will be a root. And the spinach is kind of hard to tell. So let's see, right here, if you can see the bend, that will be the root, and then the rest will be the shoot. And then right here, you can only see that these only have the roots. And so these are just more pictures of how everything looked. This was the spinach, and then this is the sweet corn. So I added these because I thought they were really cool looking at how everything, like this is all fungus and mold, and then you could see here like how some of them have a double shoot, and then how some of them had only a root growing, and then some of the spinach like didn't even germinate.
Yeah. So, like Caitlin said, a lot of the spinach didn't even germinate. So this is showing the percent germination. If the seed only had a root and not a shoot, we didn't count that as germination. So it had to have both. Because our spinach germination was very varied, and even the control, which is shown in the blue for both, the control only had 40% germination. So for the sake of the rest of this talk, we're only going to focus on sweet corn. As you can see, a lot of it was close to 100 or greater than 90%. So Dr. Awal helped us do some statistical analysis to compare the treatments and the concentrations. The first thing we did was an ANOVA analysis. So this is basically these p-values lower than 0.05 are showing that this is the means of the different factors we're looking at are statistically significant. So for sweet corn, the first extract, just looking at the roots, the different types of manure were significantly different, the different treatments were significantly different, and there was a combination of manure and treatment that was statistically significant. We're only going to focus on the manure and the treatment following this presentation. For the shoots, only the treatment was significant, as shown by the higher p-values for manure and the combination. So then we did a Tukey test, which basically looks at the means and tells you if between whatever you're in the group that you're looking at, if there's a statistical difference between the groups that you're looking at. So the letters correspond to a group, and each group is statistically different from the next letter. So in this case, chicken had statistically significant difference from dairy and lower type. Likewise, the control and 25% concentration and 12.5% concentration were different from 50 and 100. 12.5 and 50 were different than 100. So the letters tell you the groups of differences within each analysis. Yeah, so we can see chicken manures produces, on average, longer roots than the other two, and the lower concentrations are better than the higher concentrations. And this is a pretty, not normal, but this pattern is consistent throughout a lot of the data. Well, not for shoots, but so all of the three different manures were the same not different from each other, and then again, the two lower concentrations improved shoot length over the higher concentrations. We repeated the same thing for the second extraction, roots and shoots. I think these should all be highlighted, even the zeros. So all statistically significant. Again, chicken manure showed on average better, longer roots than the other two manure. And in this case, the only difference was with the higher concentrations for the second extract, the root growth. And then shoot growth again, chicken manure produces the longest on average shoots, and control and 12.5% concentrations of manure improve shoot length over the higher concentrations. So looking at a comparison of the first and second extract, so again, we would expect to see better growth from the second extract. It's more dilute, but we don't see that for dairy and Milorganite. And I think it's safe to say that there's an element or a combination of elements in the manure that's phytotoxic to the plants. In this study, we didn't pinpoint which one. I think that would be good for future work. But even at a dilute concentration, there's still elements present in the manure that's toxic to the seeds. For chicken, however, that's not present. So we see pretty significant difference between the first and the second extract. So, you know, you could recommend apply the manure and immediately irrigate to dilute some of the toxic metals or other elements. It's hard to know what is causing the toxicity, but so basically we found that chicken manure was the best out of the three, but the control seeds did grow really well on their own. So the difference is pretty slight between 12.5 and 0. Normally they were close, but if you're only looking at the three manures, chicken is the best. And then the 100% concentration was significantly at the lowest average root and shoot length. So if you're going to apply 100% manure, you're going to see, it's going to take longer to germinate, and you're not going to have as productive seeds. Spinach germination, like I said, we didn't include in this presentation because it varied a lot, and also the control was at 40% after 5 days. So just comparing the two seeds, spinach is going to take longer than sweet corn. And I think in the future we could see if another dilution, you would see the same trends with chicken manure. And even with the other two, maybe it'll start to increase if the toxicity goes down in a more dilute extract. And moving towards identifying the toxicity of individual elements, because in this there's a lot of different things in the manure. We didn't pinpoint exactly what's causing the toxicity, if it was copper or any other element present in the manure. So I think that would be a good direction to go in the future for the seeds. So there was a lot of help for this project. There was a lot of measuring. 2,000 seeds had to be measured for a root and a shoot. So a lot of people helped, and thanks to everyone at UT. So with that, any questions?
Any question for the team?
Why did you choose those two seed types?
Can you repeat the question, please?
Yeah. The question was, why did we choose those two seed types? And the answer is that they were available to us. So,
Because the germination rate, if they consider the germination rate, or
compared to doing the experiment.
Yeah, we didn't consider any other seeds because this is kind of what we had available to us.
Any other questions for them? If you don't, I think they put us right back on time. So we're really 10:30 right now. We're back on schedule, right? So our next speakers are Lassie and Carrie. And they are going to talk to us about the effect of climate
on radiation and ground fluxes of different ecosystems. So with that, and again, this is another a joint effort between Prairie View and UT Austin.
Hello everybody, how you doing? I am a Prairie View undergrad student, so this was pretty interesting to embark on with a PhD student from UT Austin. But my name is Carrie Calloway, and I'm Dr. Robinson. So we decided to understand the effects on climate through radiation, through ground flux, and the different ecosystems that play a part in, as we plotted different graphs across the United States. So understanding the overall balance in the total radiation of energy and receiving by the Earth from the Sun. It's pretty much Earth energy budget describes the balance between the radiant energy and the reaches of Earth from the Sun and the energy that flows from the Earth back out to space. The two major components that must be investigated to determine if the Earth energy budget is balanced is the incoming energy from the Sun and the outgoing infrared radiation from the Earth out to the atmosphere. Understanding where this energy goes and helps us understand natural processing taking place.
What is energy? What is energy?
What is energy? Energy. Ooh. It's a good question. What is it? Which Professor May was a big component of this. So if I'm going to ask anybody what is energy.
Radiation, right? Form of energy. Solar radiation becomes light, and
right.
The radiation itself is energy. That's your talking.
Yes.
Thank you for that clarification, Dr. Ray.
By the way, Dr. Ray is the mentor for this on this project for the team. So.
Yes. The research objectives for this study is basically understanding how the net solar radiation that's incoming, as well as the ground flux radiation, how different ecosystems and climates are impacted because of probably because of their geographical location, their climate, ecosystems, as well as the characteristics of the regions. And why this is important is because the solar radiation and the energy balance impacts the biosphere as well as water and carbon cycles, which therefore inform other climate processes. And it is very important to understand this information as well as, especially for net radiation and ground flux radiation, these are input parameters to understanding different water cycle attributes such as evapotranspiration. So having a better understanding of what trends these values have in different ecosystems and climates can help for better input data for future predicting climate models, and thus trying to understand trends in these systems have an advantage. So how are these energy fluxes measured? These energy fluxes are usually measured using an eddy covariance tower, shown here. This is a picture taken by Dr. Ray of the PDAMU eddy covariance tower measurement. And the basic principle is that this tower measures the air velocities and different eddies formed by by the turbulence of air past a single moment at a period of time. And this difference of air molecules moving past the sensor allows for calculations using covariance of different fluxes such as water vapor, greenhouse gases, as well as solar radiation and temperature. And basically, data from eddy covariance towers are able to log data over certain periods of time. So many of these data are logged on a half an hour basis over many years. And a collection of eddy covariance measures have been collected and publicly uploaded in an AmeriFlux database, which Kim will talk about.
Yeah, so we use the AmeriFlex database, which is a website that provided this information, a majority of our information that we pulled from. And it pretty much, she pulled the data and input it into a program that allowed us to understand, again, the ground flux and the temperature and how that affects within each other. So pretty much the website that was used is out of University of Berkeley, provided by Bias, if I'm not mistaken. But we used the time periods between 2016 and 2020, pulling that data that was available. We had some issues, of course, but we got through it. So some of the ecosystems and the different geography locations that we provided, again, throughout the United States. So we found that, as I mentioned, we ran into some issues. And originally, we pulled all of the data from this profile, and it outputted a lot of negative database that was under negative 9,000, as you could see, and needed to be removed from the time frame. So she spent a lot of time actually going back into the Python profile and removing the data. That came up with a visual trend of all of the data. Certain data rows are unavailable for some locations, so we pulled from different, like I said, different places. We ended up narrowing it down to a total of 8. But we pulled from probably a total of 16 originally, and a lot of that didn't have the necessary data to make the graph that we needed. So we went back and forth and eventually came up with what we have.
I also wanted to mention that these are basically different locations where eddy covariance towers are present in the United States. And so this database kind of accounts for where these eddy covariance towers are measured. And depending on the PI or the investigator, they have the ability to upload the data onto the server, and this information is publicly available. So if you make an account with the website, you can actually download the data. Like anybody can download the data to analyze or further process the data. And so one of the major questions, or one of the major issues, was to figure out what tool was best to process such large amounts of data. This is half an hour data based over many years. So one option was using Pivot on Excel, but unfortunately my computer did not have enough memory to actually open and manipulate such data, large data files. And so ultimately we had to work on writing a Python script that was able to read all these values, convert it to a data frame, and then make that data frame readable to the kind of inputs that we wanted. And so using different functionalities of Python, such as the resample tool, we were able to take those large values and convert it to daily readings instead of on half an hour readings. And we were able to then process that data over different amounts of time that we were interested in looking at. And so one of the first kind of hindrance that we ran into was understanding what all those values meant. And by convention, the negative 10,000 values are supposed to be removed. They're basically when there's no reading taking place, that's like a value that is inputted. So initially, without understanding that, plotting all the data, we were not able to observe any foreseeable trend, as well as that this information was not usable since we weren't removing the negative 919 values. Upon closer investigation, without removing the negative 99 values, we were still not getting appropriate trends because it was very important to be able to average the right data in such a large selection of data without actually being individually going and understanding what each reading was. So after removing the negative 999 data, as well as deciding on looking at just 1 year of information, so that we're better able to understand the trends which correlate between different data sets. We decided to focus on 2019 because that was the closest year where more data was available, and many of the databases actually had information on it, as sometimes some databases had missing years and missing dates as well. So understanding what to study and how to study it was a major part of this endeavor. And so finally, thanks to Dr. Ramre, we were able to, this is just a map of the locations that we were looking at. And a lot of the reasons why we selected these particular ecosystems and this particular locations were data availability, because that was our major constraint in being able to process the data. And so Sherry will talk more about the different ecosystems that we selected.
Yes, so one of the ecosystems that we selected is a woody savanna. One area is Santa Rita Mesquite, which is in Tucson, Arizona. This area is more warm wintered, and a large area is flat unforested grassland. This area also is not known for necessarily growing. So as I go through these, I'm going to be allowing you to understand the canopy covers within these regions and the percentage rate of them. So in Santa Rita, there was a 30 to 60% canopy cover between the forest land. This pretty much just means throughout the year what is covered on the land, or what actually grows, as well as in the next market in the woody savanna, which is Tucson Ranch, which is in Nevada, located in Nevada. This area is classified as woodland, or private. It is privately owned, and the majority that grows here is dominated by blue oak trees. Over 40% of vegetation of the blue oak tree is grown here, as well as pine trees. It also has up to 30 to 60% of the canopy cover rate between, and it is more of a Mediterranean atmosphere with mild to dry and very hot summers. So the next one is going to be open shrubland. So these two are open shrublands, which one is located in New Mexico and the other one is located in Utah. The canopy cover within New Mexico is up to 10 to 60%. It's more of a desert feel. It's very cold winter time. There's not much that grows here, but woody vegetation and shrubs, tall shrubs and short shrubs. The vegetation in Utah are lands and woody vegetation. That canopy covers, again, up to 10 to 60%. Foliage and evergreens. The climate there is more warm summers, and significantly precipitation is all season. So it has a very high precipitation rate between all of the different seasons year round. So the next one with ecosystem is going to be, I might be pronouncing this wrong, so forgive me, Deciduous broadleaf, I'm just going to say broadleaf forest. So broadleaf forest, one location is in Boston, Massachusetts.
Easy one is evergreen.
Evergreen, that's the best way to put it. So the evergreen area
One location is in Boston, Massachusetts, which is it's the Elon Landley Experimental Farm. They have warm summers and also have high precipitation all season round. I found that they're covered up to 60%, and their lands are dominated more by woody vegetation. And then the next atmosphere is in Virginia, which is the harvest forest. And they are a more humid area with very hot summers and also dominated with land with woody vegetation to actually cover 60%. The next area is going to be in Oklahoma. They actually are known for growing a canola crop. And they also have a very humid atmosphere and hot summers. It's not really dry at all in this area. And they didn't really give a percentage, but this particular area is one of the largest, one of the largest atmospheric observations. So that's something to notate. So they do cover a lot of land that they observe in Oklahoma. And it's up to 160 acres of cattle and pasture land in that area as well. And the next area is actually California. In California, next to the Delta River, the Blue Island Alpha area, which is a cropland that is more of a Mediterranean feel with mild, dry, and hot summers. So the next area is in North Carolina, which is the Alligator River. Majority of what's growing here is corn and soybeans, and they have a lot of wildlife that resides in this area as well. It's very humid, and they have hot summers, not really a dry season there. It's close to the waterland there in North Carolina, and the next area is actually in California, and they're known to growing corn. This is also a Mediterranean area. As you can tell, what I would like to eventually study or understand is I'm seeing that they're growing a lot of corn in the Mediterranean areas, and in a lot of the humid areas they're growing a lot, yes, they're growing also a lot of corn. So just understanding the different atmospheres and areas and how they're growing and how what we're studying affects the growth and vegetation there.
So these are basically the results. One thing is that a lot of these are preliminary understandings by plotting different variables that we had, as well as so none of the observations are something that I have statistical backing with. Currently, these are just observational inferences to understand basically what's happening or what's probably happening with the data. So in the period of 2019 to 2020, this is the woody savanna region that Carrie had talked about. And we can definitely notice that in regions with that the net radiation tracks with temperature, which makes sense because the radiation would be impacted by temperature, but as well as an observational inference is that the humidity varies the net radiation that is ultimately received, and this is probably due to the energy balance that's present because a lot of the heat ends up going into latent heat or sensible heat, which is why when there's a greater fluctuation in humidity, there's a greater fluctuation in the net radiation as well, net radiation and ground flux radiation. We can also see that during the mild, dry summers here that there's a higher gap between the net radiation and the ground flux data in a drier climate. In the open scrub regions, which are some of them are the desert regions, where the other one was the Utah very cold winters. You can see that this shows a similar trend with the with similar temperature trends, but at the same time we can see that the ground flux values as well as the radiated heat values are they're closely tracking, which is probably a function of the crop cover that's present within in such low density shrubbery area. In croplands, we can see that uh, areas with um, drier climates have a higher difference, even with a lot of cover. Thus, the climate conditions really impact what the difference between the net radiation and the ground flux values are. Um, and um, in deciduous forest, we can see that there is lower values of ground flux in comparison to other ecosystems. And this is a significant reason for this could be the canopy cover, which is limiting the amount of net radiation that actually reaches to the ground to be able to absorb the heat present in the ground. As well as in wetlands, we can definitely see a very much lower trend of ground flux radiation. This is because in wetlands, a majority of the land is covered by water, and thus there is not enough, there's not as much ground flux heat that is being absorbed to the ground. And thus, radiation and ground flux are inputs to understanding evapotranspiration, and thus understanding which ecosystems and what climate models can have the ground flux as a negligible term, which is very often an assumption that's used. It's important to see that in some ecosystems we cannot neglect the ground flux values, and thus understanding ecosystems and climates really there is an advantage to understanding this difference. And this is just an overall comparison of different ecosystems and what the tracking net radiation values are. We can see that in the specific regions that we have selected, the woody savannas as well as the open shrublands have a higher net radiation present. These are probably due to the locations as well as the temperatures that are often present in those regions are. As well as for ground flux, we can see that the croplands have very high ground flux, and thus it's not a term that we can neglect in various climate models, and it's important to understand and measure the ground flux in cropland ecosystems as well as but whereas we can see that there's lower values in other ecosystems, and thus this gives us a more ideal picture that all of these trends are kind of tracking over the years. So this also shows us that just understanding year by year also has a benefit because we are seeing similar trends over the past few years. And basically a summary of kind of the work and understanding is that with big data and so much information available, we can do a lot of different studies. And one of the very major takeaways is that trying to select what to study, what the research question is, to understand these large data sets is very important. And while there's a million things we can do with all the different parameters that were put in the database, we selected a few that might be interesting to investigate. And thus, there's a lot of potential in using different locations, using different ecosystems, using basically other different variables, trying to track and correlate statistically what weather conditions or climate conditions impact these ecosystems. And so definitely there's a lot of potential in this kind of analysis and study. And just trying to hit on a few future potential studies is using other weather parameters, using ANOVA analysis to see if any of these relations are statistically significant, using other regions and broader time periods to be able to create an actual trend so that we can use it in future models and kind of have a definite trend values that we can use for ground flux and net radiation data for future models. And these are potentials of what can be accomplished by such powerful measurements and public databases, which is very exciting. So I would like to thank everyone who helped us, and especially PDA and me for hosting us. being able to do this project, and Dr. Ron Ray for providing insights and guidance throughout the process. And also thanks to UT Infews team for letting us come here and be part of all of this. So definitely thanks.
Thank you. For the sake of time, I mean, if we have a question, we can leave it after Kate's and Jaden's presentation. So, which is gives us to the last section of the program, which will be talking about two topics: the fourth provision amendment patent rights on leaf, chlorophyll, and NDVI measurements. So another joint effort between Prairie View College of Agriculture and UT College of Engineering. And Jana and Kate will be talking to us.
Good morning, everyone. My name is Jana Lede, and this is Steve. And today we're going to be talking about the effects of organic amendment types and rates on leaf chlorophyll and NDVI or street corn. So what is NDVI in strategies, right? NDVI can normalize different vegetation index, and it measures the plant's amount of absorbed visible light and reflected infrared light. So if you look at the bottom picture here, you'll see that a -1 reading to 0 is a dead plant, a 0 to a 0.33 is an unhealthy plant, a 0.33 to a 0.66 is a moderately healthy plant, and a 0.66 to 1 is a very healthy plant. Now, SPAG reading is a social plan analysis development, and this tool is designed to help producers improve the crop quality and increase the crop yield by giving them a reading of the amount of chlorophyll that's present in the leaf. So the research motivation and objectives of this project is to study the effects of different organic manure types and rates of application of tree corn plant health. So we use this by monitoring soil plant health monitored using NDVI and SABRE measurements. The little data that is available for organic manure in Texas helps farmers better manage their crop and minimize excessive loss that will impair water quality. And the objective is to compare NDVI and SAT readings between manure types and amendment rates, and assess the relationship between NDVI and SAT readings. So we saw this earlier in a different project, but I just want to go a little bit more in depth on this one. So the green plots are the chicken manure, and the blue plots are the dairy manure. And so for the zeros is the control, and the 1, 2, and 3, the 1 being half of the treatment rate, and the 2 being the actual treatment rate, and 3 being the double treatment rate. And the yellow ones, the W's, are the plots about irrigation and manure. So this is the NDVI reading, and as you can see through May 12th, June 1st, June 15th, and June 28th, that the controls are a little bit lower than the C1 through C3 and D1 through D3, because you can definitely see that the treatment rates gave a more higher rating that we want closer to a healthy plant. So the control is giving us a moderately healthy plant versus the treatment rates that are giving us the very healthy plants that we're looking for, closer to that 1 level.
Okay. And SPAD readings follow. SPAD readings follow a pretty similar trend. As it would be expected, the SPAD meter reading measures the absorbance of chlorophyll, so it's still a light-based measurement. You kind of expect them to be the same. You can't really see a whole lot of difference on the May 12th date, but as time moves on, the chlorophyll develops more so with the chicken amendment, and also more so with higher rates of application of that chicken. And that follows too for the dairy, and especially compared to the plots without any irrigation or amendment, there's significant improvements in the chlorophyll concentration. And so one thing that we did beyond this was to look at the statistical significance of the chlorophyll and the NDVI readings with respect to changing the manure type and the treatment rate. And so this was presented earlier, the Tukey test, which is done after an analysis of variance and a ANOVA test, which will compare your dependent variables such as the chlorophyll percentage or the NDVI reading versus a couple other variables such as, for example, using either chicken or manure and the 4 types of rates that we used, that the Prairie View used. And so what we found with the chlorophyll and NDVI is that there was still a difference between the amendments being used between chicken and manure, where chicken basically showed to have a healthier plant when it comes to the NDVI that was measured and then the chlorophyll content. And then also the treatment rate had statistical significance between the highest rate and the lowest rate for both the chlorophyll content and NDVI readings. That is marked by the letters. So all the letters A would be a homogeneous group of the mean, and then that is all statistically related to one another and different than the other letter B in both plots. And another goal of our project was to see if you could relate leaf chlorophyll content and NDVI readings. And so we tried 2 methods, just a simple linear regression done in Excel, and then also a random forest regression that Dr. Wall walked us through using Python, this is a decision tree model that essentially is used for determining nonlinear relationships. If this were to be successful, as you can kind of notice, there's not a lot of correlation between either of the 2 readings, and if the random forest regression model were to be successful, all of the green dots would be on that line, because it essentially provides a test score and a prediction value based on that test, and it was unsuccessful, and so based off this study, there was no correlation found between the 2 readings, which it is possible that there could be, because I had mentioned they're both light-based, and so maybe there is something more to be found there. But in this case,
what does the NDVI measures?
Sorry?
What does the NDVI measures? What are you actually measuring?
Oh, it measures the difference. We could go back, actually. The equation is up on the top right there. So a healthy plant will absorb more visible light, and so it will reflect less, and it will reflect more near-infrared light. A healthy plant will. And so if you look at, for example, down here, for a healthy plant, it is reflecting a lot of near-infrared light and absorbing a lot of visible light, so you get a higher value for NDVI. And so, no correlation was found between the 2. And so some conclusions from this work that we conducted was that NDVI and SPAD readings are not significantly related to one another, that manure type and rate do have an impact on NDVI and SPAD readings, implying their effect on overall plant health. However, so did the repetitions. If you remember the plot, every plot was done in triplicate, and each repetition also had, according to the Tukey test, a separate homogeneous value for their mean. And so that is showing that there's a lot of variability just between the spatials. And so there's some future work to be done of comparing this type of data with perhaps other soil and plant health parameters to try to understand these relationships. And thank you, especially to the TVA and staff, Dr. Wall, Hassan, Dr. Pito, and Dr. Ferris.
Thank you. For the sake of time, I would like to move to the next presentation. By the way, there is a correlation between, but it's not at the level that you want. We would like to move to the last presentation by Kate. So, and you see the title there, Assessment of the NASA SMAP Soil Moisture Problem.
Hello, everyone. I'm Kate, sir. We'll be talking about NASA's SMAP Soil Moisture Prize.
Kate alone.
So SMAP stands for Soil Moisture Active Passive. This was a satellite launched by NASA in January of 2015, and it measures the soil moisture content in the top 5 centimeters of the entire Earth's surface. It does this by an active measurement, which is a radar that emits wavelength at 1.2 gigahertz down to the Earth and monitors the signal that is received back. And then it also does it passively by just monitoring with the radiometer the passive wavelengths being emitted from the Earth's surface. And using these two values, it's able to calculate a surface soil moisture content. So potential applications of this product are numerous. Knowing the global soil moisture content and trends could allow you to better